Let's wait. I don't know why I'm unable to record this. Recording is yet not coming. Still not coming. Okay, so today's class, after we have seen the expressions or we have derived the field equations for parallel plate waveguides, we'll now move on to deriving the field equations in rectangular waveguides. And in the last section for parallel plate waveguides, we have seen that we can divide the solution of field equations into two groups, and we name them as modes. One is TE mode, the other is TM mode. Okay, TE modes are transverse electric modes, TM modes are transverse magnetic modes, and we classify them as depending upon whether EZ or HZ is present or whether EZ or HZ is absent. Either one of them, we need one of them to be present for the ways to propagate in a rectangular waveguide. Now, that we have seen how we can classify this into two groups of field, one as TE waves and TM waves. Same thing we are applying to rectangular waveguides also. For parallel plate waveguides, we have only one set of boundary, that is top and bottom. Whereas for rectangular waveguide means you have added one more set of boundary, that is you have enclosed the wave in a pipe, rectangular pipe-like structure. At one end you have the input, the other end you get the output. So you have the boundaries top and bottom metal sheets and front side and back side. So left and right, the openings are there for the source to be input and destination to take out the output. Okay, and see, for these are the general sets of equations which we have derived earlier for a rectangular waveguide. This I have written it once again. You can see on my screen this field equations for Hx, Hy, Ex, Ey. And what do they stand for? H stands for magnetic field, E stands for electric field. X and Y denote the directions, and always Z is the direction of propagation. Okay, and we assume that. So either Ez or Hz has, both of them cannot be zero at the same time. Otherwise, what happens? All the fields would vanish. We can look at the equations. See, each one of them will contain Hz and Ez. Okay, all of them. Hx is equal to minus gamma by h square dou Hz by dou x plus j omega epsilon by h square dou Ez by dou y, like that. Each one you have a component of Hz and Ez. That means if both are zero at the same time, all the fields would vanish, and such a condition cannot exist. Waves will not propagate. So either one of them, ഒരെണ്ണം ഏതെങ്കിലും ഒന്ന് HZ ആയിരിക്കണം. അപ്പോൾ you will get magnetic field and electric field equations. Okay, so this you have in the previous class also. I had stopped here. We had done up till this. So refer to those slides for this derivation. How we reached them? We started with Maxwell's equations, applied boundary conditions and solution of equations to arrive at these. Okay, now these are the general equations we obtain for a rectangular waveguide. Now, we know that any field, electric field, in terms of the variables x, y, z, can be represented as its magnitude and phase, like this. That is Ez dash xy e raised to minus gamma z. Okay, in general, any electric field or magnetic field can be written in its phasor form in terms of its magnitude and its phase. Gamma is the propagation constant, as you know. And here, in the earlier case for parallel plate waveguides, or starting with this finding the solution for RWG, we had substituted Ez dash as equal to x into y. This also you can refer to those previous slides. Okay, please do. So Ez dash, that is for deriving the solution. you substitute it as z dash is equal to xy, capital XY, where x is a function of small x alone, variable x alone, and y is a function of variable y alone. Okay, small y. So x and y, capital X and capital Y are actually f of x and f of y. Okay, remember that. And for the ease of expression, we have simply written them as x, y. Okay. So e dash is x equal to a function of x into function of y, which is equal to capital X is a function of x alone and capital Y is a function of y alone. So Ez dash is equal to x into y, where we had obtained the solution as using the method of separation of variables. We had solved the differential equation and we had obtained the general solution C1 cos Vx plus C2 sin Vx into C3 cos Ay plus C4 sin Ay. Okay, C2, C3, C4 are constants. And similarly, if you want Hz dash, magnetic field also can be similarly written as equal to xy with d1. Instead of these C1, C2, C3 constants, you can use another 4 as constants. Okay. This is a general expression for the solution of Ez dash. All this is coming in the previous discussion. Okay. Now, so for TM waves means magnetic field will be entirely transverse to direction of propagation. That is Z direction. Hope you are understanding. Hope it is clear to you. Okay, what is written on the screen. If there is any problem, please do tell me. Okay. Don't hesitate. Okay, so for TM waves, the magnetic field is entirely transverse to the direction of propagation. That is Z direction. Okay, no magnetic field in the Z direction, that is Hz is equal to 0. So by substituting Hz equal to 0, we can determine the expressions for Hx, Hy, Ex, Ey, and using Ez dash is equal to this format, capital X, capital Y. Okay, where capital X is equal to C1 cos Bx plus C2 sin Bx, capital Y is equal to C3 cos Ay plus C2 sin Bx. Okay. This we have obtained. So in the first set of equations, if it is TM waves we are considering, first we will consider TM type of waves. After that, we will go to TE waves separately. Okay, either one of them is enough because the other one easily follows from the other. Same procedure, except that you have to simply substitute, interchange E, H, etc. So how can we obtain the solutions for TM waves in rectangular waveguides? TM waves means Hz is 0. That means here you can give Hz 0. That means this first term for Hx will be 0. Here Hy, Hz is 0 means first term will be 0. Hz is 0. Ey, the second term will be 0. So all these field equations will have only one term, depending upon whether Hz is 0 or Ez is 0. Ez is 0 for the other case, that is TE modes. Here we are considering TM modes. So now first what is the step? You have to substitute Hz is equal to 0. If it is TE mode we are considering, then you have to substitute Ez is equal to 0. That's only difference. Okay. So first we will consider TE modes. You give Hz is equal to 0. That means each one of these variables Hx, Hy, Ex and Ey will have one term only. Okay, because here the first term 0, this first, here second term 0, and this second term also 0. Okay, so there is only one term in each of the field equations now for our particular case. And we also have substituted Ez dash is equal to, of course, Ez should exist. Otherwise, everything should be will be. Okay. So Ez dash is equal to xy, where x is of this form, y is of this form. It's a function of, both are functions of cos and sine, where b square, this is yet another substitution we had done. We had substituted b square is equal to h square minus a square, and What is h square? That also we had substituted earlier as sum of gamma square plus omega square mu epsilon. Okay. This expressions, these assumptions, not assumptions actually, we had substituted these variables earlier. B square, capital B square is equal to h square minus a square. What is a and what is b? These two constants that are coming in the solution for Ez. Then small h is given by h square is equal to gamma square plus omega square mu epsilon, where gamma is the propagation constant. Now, C1, C2, C3, C4, we have to obtain them. That is what we mean by solving. These constant we have to obtain to get the complete solution. How can we obtain them? C1, C2, C3, C4 can be obtained by applying boundary conditions. So this is how the rectangular waveguide looks like. See the figure. Okay. How can we obtain the solutions? By applying the boundary conditions. We know the boundaries exist at x equal to 0, x equal to a, y equal to 0, and y equal to b. These are where the top and bottom levels, front and back levels for the metal sheets or the pipe boundaries. So that means at these boundaries, boundary conditions, we know that the electric field is 0 or continuous. Ez dash is equal to 0. Tangential component is continuous, normal component is discontinuous, that we have obtained. So applying that, Ez dash is equal to 0 at y equal to 0 and y equal to b. Similarly, Ez dash is equal to 0 at x equal to 0 and x equal to a. Okay. Now applying these boundary conditions, what is our expression actually? Ez dash is equal to capital X into capital Y, which is C1 cos bx plus C2 sin bx into C3 cos ay plus C4 sin ay. Okay. Now, first you take the first condition, that is x equal to 0, y equal to 0. For the two variables x and y, you take the first initial condition at x equal to 0, y equal to 0. Give x equal to 0 here. That means cos bx. X equal to 0 means cos 0 becomes 1. So C1x is C1 plus C2 into sin x equal to 0 means this term will become 0. Here, C3 ay. Y equal to 0 means C3 will be there. Cos 0 is 1. Sin 0 in the next term, it will be 0. So what do we get from the equation by applying the first set of boundary conditions? C1 here and C3 here. The other two being 0. That means product will be C1 into C3. C1, C3 is equal to 0. At x equal to 0, y equal to 0, Ez dash is equal to 0. That means you substitute as equal to 0, C1, C3, their product should be 0, which means we can, of course, take C1 equal to 0 and C3 equal to 0 for our ease of expression. Okay, you can make your process simpler. So we will just assume either one of them should be 0. There is nothing wrong in assuming that both are 0. Okay. So we assume that both constants C1 and C3 are 0 as their product is 0. So what do we get? C1 is 0, C3 0 means the expression becomes C2 sin bx into C4 sin ay. Okay. C2 sin bx, C4 sin ay. Now we can apply the next set of boundary conditions. What is that? X equal to a, y equal to b. That can be applied. So you applied the first set of conditions, got C1 and C3 as 0. Then now to obtain C2 and C4. At x equal to a and y equal to b, again Ez dash should be 0. That means you give x equal to a here. That means sin b small a, C2 sin b small a, C4 sin a small b. Okay, x is equal to a, y equal to b. That is given in this expression for Ez dash, the last expression that we obtained. So that should be equal to 0. Sin BA sin AB is equal to 0. So what do we get? If that product is 0 means either one of them should be 0 or both can be 0. So that we can equate for Ez dash is equal to 0, sin BA into sin AB should be 0. So if sin BA is 0 means BA should be some multiple of what? Pi, 180 degree. But sin 0. So BA should be some multiple of pi, which is equal to n pi, where n is an integer. Similarly, sin AB is equal to 0 means AB should be some multiple of pi. Again, we choose another integer m. So AB is equal to m pi. So BA is equal to n pi, AB is equal to m pi separately. That means from which we can write capital B is equal to n pi by A and capital A is equal to m pi by B. Okay, hope you are following that. Capital A is equal to m pi by A, capital B is equal to n pi by B. What is small a and small b? Dimensions, the length and height of the or width and height of the rectangular waveguide that should be given to you. They are dimensions in centimeters, like that is height of the pipe and its width, A and B. Okay, if they are known for m and n, you can have different values. Any value you can give starting from 0 to infinity. They are integers. Okay, so you get an expression for B, capital B and capital A, so that Ez dash can be written as C2 C4 into sine m pi by ax into sine n pi by b y. Okay, that way you can write instead of that is substituting b and a in the earlier expression, so that the complete expression for Ez now becomes Ez dash is to minus gamma Z, which can be written as, instead of C2 and C4, you write it or substitute E naught, where E naught is equal to C2 C4, and taking it as the amplitude. We need not now find out C2, C4 because their product we have as the amplitude, and we replace it with E naught. And we have obtained solution for A and B. So sine m pi by A into x, sine n pi by b into y, e raised to minus gamma z. Okay. So if you want, you can find out dou Ez by dou y and dou Ez by dou x from this expression. You have expression for Ez. So for example, I have done dou Ez by dou y, that is partially differentiating Ez expression with respect to y. What do we get? E naught into a sine m pi by ax. It does not depend on y. That means for the next term which depends on y, taking the partial derivative. So here the constant is n pi by b. So first you write n pi by b into E naught into sine n pi by ax as such. Then for partial derivative of sine n pi by by, it becomes cos n pi by by. Okay, into e raised to minus gamma z. That's how you find out dou Ez by dou y. If it is dou Ez by dou x, you simply have to partially differentiate the first term, sine m pi by ax. That means here it will become cos m pi by x into m pi by a. Instead of n pi by b, you will write m pi by a. That's all the difference. Okay, so we have an expression for Ez now. Can we now get the full solutions, complete solutions? Now the field expressions, we can now write taking that one term alone, because we have already put Hz to 0. That means in the first set of equations, they become, after removing those terms which are becoming 0, you write them once again. Hx, hy, ex and ey are once again written here in terms of either that is in terms of Ez only, because Hz has become 0. TM waves we are considering, that is why. Okay, remember, or if it is TE waves, it should be the other way around. So it is TM waves we are considering. That means Hz has been put equal to 0. Only the partial derivative with respect to x or y for Ez remains. So dou Ez by dou y is coming for Hx, for hy dou Ez by dou x, for Ex dou Ez by dou x, and for Ey dou Ez by dou y. Okay. So you find out dou Ez by dou y, which we have already found out here. See, you need only write it directly here. Similarly, dou Ez by dou x, I explained just now. So substitute that. You substitute dou Ez by dou y, so that you get the next expression like this. You expand it, j omega epsilon by h square into j omega epsilon by h square into n pi by b into E naught into sine n pi by ax cos n pi by by e raised to minus gamma z. Similarly, for hy, you find out dou Ez by dou x and write the complete expression. So each of them has been written down here simply by taking the derivative of Ez with respect to x or y. Okay. So now these are the field expressions for TM mode. We have obtained the field expressions for TM mode in a rectangular waveguide. 4 solutions are there: Hx, Hy, Ex, and Ey. Okay. Now what? We know that x square minus a square is equal to b square. This we have written earlier. And small h square is equal to gamma square plus omega square mu epsilon. And we know that gamma square is equal to h square minus omega square mu epsilon. That is, instead of h square, we can write a square plus b square. Okay, from here. So you write a square plus b square minus omega square mu epsilon. So that gamma square is equal to, what is a and what is b? Just now we obtained them as m pi by a and n pi by b. Okay, you make that substitution here, so that gamma square becomes m pi by a whole square plus n pi by b whole square minus omega square mu epsilon. So now we have an expression for the propagation constant in terms of the dimensions a and b and m and n. So gamma is square root of m pi by a whole square plus n pi by b whole square minus omega square mu epsilon, which is the equation for propagation constant for TM mode in a rectangular waveguide, where m and n represent the number of half cycle variations, or we simply call them as the indices. They are actually the number of half cycle variations in the x and y directions. So your question will be, derive an expression for propagation constant for TM mode in a rectangular waveguide. So first you have to get the solutions, then this is how you get the expression for gamma propagation constant in terms of m, n, a and b. Okay, so this is the expression for propagation constant. Now what? Now we can have any possible value for m and n. First, let us start with 0. Both m and n are 0. Suppose what happens in the field expressions here. These are the field expressions which we got. M and n are both 0. What happens? Here, n is equal to 0 means n pi by b is coming. So hx will become 0. Second one, hy, m pi by a. M equal to 0 means that also will become 0. We need not look at the remaining terms because already m and n are 0. Then same case for ex and ey. M is 0 and n is 0. Okay, all the 4 equations would become 0. Nothing would exist. So m equal to 0 and n equal to 0 will make all the fields vanish, which means that such a condition is not giving us anything, any result. It cannot exist. So we do not take m equal to 0, n equal to 0 at all for Tm. Remember, it's for Tm only. For Te, it will be different. So first condition, m equals smallest integer, m equal to 0, n equal to 0. That is, all fields will vanish. Okay, it will not exist. Now, one of them is 0, the other one not equal to 0. M equal to 0, n not equal to 0. N can be any value, 1, 2, or 3, but m equal to 0. See what happens there. Here, m equal to 0, but n not equal to 0. So here m equal to 0 means, what about hx? M equal to 0 means sign becomes 0. That will be 0. About the second one, m equal to 0 means that will already become 0. Then ex will also become 0 because m pi by a is coming here. Then last one, there also m equal to 0 means sign term will become 0. Ey will also become 0. That means second condition, m equal to 0 and n not equal to 0, here also all fields will vanish. It is also not possible. Now what about the other way around? M not equal to 0 but n equal to 0. Same thing happens. See, n equal to 0 means this will become 0, n pi by b is 0. Last one will also be 0, n pi by b is 0. Similarly, m not equal to 0 but n equal to 0 means the sign term in hy here. And sign term in Ex will also become 0. Same thing happens. All fields will again vanish. So m equal to 0, n equal to 0 is not at all possible for any case. For the three cases, all fields will vanish. So we do not take that case m equal to 0, n equal to 0. So, m or n cannot be 0. We have to start with 1. The last value or the first value we start with is always 1 for m or n. This is why, because for m equal to 0, all fields will vanish for any case. Okay. So we take m equal to 1 and n equal to 1, and we call the mode or configuration as tmmn suffix mn, tm suffix mn, and m equal to 1 and n equal to 1 becomes tm11 mode. So which is the lowest mode possible for tm. Okay, so we'll be asked to prove that TM11 is the lowest order mode possible for a rectangular waveguide. This is how you can prove. Write the field expressions and show those conditions that all fields will vanish for all cases of m equal to 0 and n equal to 0. Okay. So lowest order mode is known as TM11. Okay. Then again, gamma square, we obtained an expression like this. Now, when this, how did we obtain this? Here, from here, we obtained an expression for propagation constant. Gamma square is equal to m pi by a whole square plus n pi by b whole square minus omega square mu epsilon. Now, take that equation for the propagation constant. So, this is the first term, we assume it is positive, that minus omega square mu epsilon. Now, what is gamma? Actually, it is sum of alpha plus j beta, where alpha is the attenuation constant and beta is the phase constant. So, propagation constant actually it is a complex number where the real part is alpha and imaginary part is beta, alpha plus j beta. Alpha is attenuation constant, beta is the phase constant. Now, here in this expression for gamma square, if the first term is positive, gamma square will be positive, isn't it? This sum, m pi by a whole square plus n pi by b whole square. If that sum is positive, omega square mu epsilon, then this will be positive. If omega square mu epsilon is very small, then gamma square must be positive and real. Okay, it will not be imaginary because the difference is always positive. That is, in that case, gamma is equal to alpha because beta is 0. If it is purely real, means beta part will be 0. So gamma becomes equal to alpha. That means no phase constant, only attenuation takes place, which means the wave is getting reduced in amplitude and no propagation. Okay, understand? If this part is this omega square mu epsilon is sufficiently small, in that case, gamma is positive and real or becomes equal to alpha alone as beta becomes 0, which means only attenuation will take place for that wave and no propagation will occur. Such non-propagators are called evanescent modes. That's a definition for evanescent modes. What are evanescent modes? Those modes which are having only attenuation and no propagation. They are simply getting reduced in amplitude, getting attenuated. Okay. When does that occur? When omega square mu epsilon is sufficiently small in the expression for gamma square than n pi by a whole square plus n pi by b whole square. Okay, that is evanescent mode. Now, suppose both the quantities become equal in the expression for gamma square. If omega square mu epsilon is equal m pi by a whole square plus n pi by b whole square, what happens? Gamma square becomes 0 or gamma is 0. That means alpha is 0 and beta is 0. There is nothing. Propagation is 0, alpha is 0, beta is 0. So no wave propagation occurs in such a case. The two parts are becoming equal. Now we'll take the third case where this omega square mu epsilon is greater than m pi by a whole square plus n pi by b whole square. Then what happens in the expression for gamma square? If this part is less, means this will be negative. So when you take the root of gamma, it will be imaginary. you will have to take a square root of a negative number. So j will come. Okay. So that is the third case. First case is when this one is positive. Second case is when both these two are equal. Third case is when this part is less than omega square mu epsilon. So at some frequency that can occur. So what happens here? At some frequency, omega c, at some frequency, say omega equal to omega c, that part is, that is becoming equal. And after that, above that value, if it is becoming, that part is becoming lesser than omega c square mu epsilon, then by equating these two, we can get an expression for omega c. What is omega c? It is the cutoff frequency below which no propagation occurs. Okay, only above that. So an expression for omega c can be obtained by equating these two, and from which we get omega c is equal to, see, equating these two and taking the square root of 4 omega c from this one. 1 by root of mu epsilon into root of m pi by a whole square plus n pi by b whole square. Okay, you get an expression for cutoff frequency. So what is cutoff frequency? It's the frequency below which no propagation occurs. So only above that frequency propagation will occur. So in rectangular waveguide is acting as a what filter? High pass filter. Okay. So here again omega c, as you know, it is angular frequency. It is equal to 2 pi into fc, where fc is the actual frequency in hertz. Omega c means you have to always multiply it with 2 pi. So 2 pi fc equal to, again once again we write the expression 1 by root of mu epsilon into root of m pi by a whole square plus n pi by b whole square. Fc is equal to, you take this 2 pi here, 1 by 2 pi root of mu epsilon into this part, cancel out that pi from the denominator and the numerator, so that you get fc is equal to 1 by 2 root of mu epsilon into root of m by a whole square plus n by b whole square. Now what is that 1 by 2 into root of mu epsilon? That we call as, that is 1 by root of mu epsilon as the phase velocity, Vp. So you substitute, instead of 1 by root of mu epsilon, you write it as Vp. Vp by 2 into root of m by a whole square plus n by b whole square. So Vp is equal to, if the medium is free space, then mu is equal to mu 0, epsilon is equal to epsilon 0, free space values for mu and epsilon, and you can calculate the velocity as that equal to, that of equal to light, 3 into 10 raised to 8 meter per second. Okay, so what is phase velocity? It is actually 1 by root of mu epsilon, where mu is equal to mu 0 mu r, epsilon is equal to epsilon 0 epsilon r. Epsilon 0 and mu 0 are the values in free space. Epsilon r and mu r are the relative velocity, relative permittivity or permeability values in the medium. Okay. So now you have derived an expression for the cutoff frequency Fc. And if you want Vp, M, N, A, and B, you will be asked to calculate Fc. You can get numerical problems for that. Okay. Now that is expression for Fc. So cutoff frequency Fc is once again written here. And we know we can also find out the cutoff wavelength lambda c, which is velocity by frequency. So Vp by Fc is wavelength. You find out that from this expression, Vp by Fc is 2 by root of m by a whole square plus n by b whole square. So cutoff frequency and cutoff wavelength can be calculated. And we also have seen that TM11 is the lowest order mode that exists. And this mode, its cutoff frequency, if you want to calculate the cutoff frequency for that mode, that is m equal to 1 and n equal to 1. You give m equal to 1, n equal to 1. What becomes Fc? Fc is equal to Vp by 2 into root of 1 by a plus 1 by b whole square. So that value will be the smallest one, because we can, the smallest values that we can give for m and n will be 1 and 1. So all values are higher than that. That means Fc will be having a higher value for all higher order modes. So 1, 1 is the lowest order mode that exists. And this lowest order mode or the mode with the lowest cutoff frequency is known as dominant mode. Okay, you will always be asked to define the dominant mode, or you will be given the cutoff frequency for the dominant mode, which means you are not directly given M and N, but you know that TM11 is the dominant mode for TM. Okay, so what is the definition for TM dominant mode? It is the mode with the lowest cutoff frequency in a rectangular waveguide. So for TM waves, it is TM11. So learn the definition for dominant mode. So again, once again, omega square mu epsilon is greater. That means gamma is purely imaginary, alpha is 0 and gamma equal to j beta. So that we can write gamma square is equal to j beta square, which is equal to omega square mu epsilon minus m pi by a whole square plus n pi by b whole square. That means beta you can write as square root of this. And you do some manipulation, take omega square mu epsilon outside the bracket or square root, take omega mu root of mu epsilon outside and divide the divide the quantity inside the square root by omega square mu epsilon. So you get inside the square root, you get 1 minus m pi by a whole square plus n pi by b whole square by omega square mu epsilon. So simplifying that, we know that we have already got that c square is equal to 1 by mu epsilon into m pi by a whole square plus n pi by e whole square. That means you can substitute instead of, see here, this quantity of m pi by a whole square plus n pi by b whole square by mu epsilon. That is the expression for omega c square. We got it from the definition, cutoff frequency definition we have obtained by equating these two. And now what we get, you can substitute instead of omega, that quantity, you can substitute omega c square. So that beta is equal to omega root mu epsilon into root of 1 minus omega c square by omega square. Now omega c square by omega square is nothing but fc by f whole square, because we know omega c is equal to 2 pi fc, omega is 2 pi f. So you cancel out that 2 pi factor and you get beta is equal to phase constant is equal to omega root mu epsilon into root of 1 minus fc by f whole square. So this is the expression for beta in terms of the cutoff frequency fc, which is equal to beta dash into root of 1 minus fc by f whole square, where beta dash is omega into root mu epsilon. You simply substitute beta dash as omega root mu epsilon. And wavelength, you know the definition for wavelength in the guide as 2 pi by beta. That's according to definition, wavelength is 2 pi divided by phase constant. So that becomes 2 pi by beta. What is beta? Beta we got just now, this one. Substitute this expression. So 2 pi by omega root mu epsilon into root of 1 minus fc by whole square, which is, now what is that is equal to 2 pi by omega root mu epsilon. That means it is lambda is equal to 2 pi by beta dash. That we write as lambda. So it is, this part becomes lambda. So it is lambda g is equal to lambda by root of 1 minus fc by f whole square. So this is the expression for guide wavelength, not the operating wavelength, but guide wavelength. It is also different from cutoff wavelength. Okay, cutoff wavelength we have another expression. This is the guide wavelength or wavelength in the guide, given by lambda by root of 1 minus fc by f whole square, where fc is the cutoff frequency. And this factor, that square root of m pi by a whole square plus n pi by b whole square, it is known as cutoff wave number or Kc. Okay, that usually you will be given Kc. That means what is given? M pi, square root of m pi by a whole square plus n pi by b whole square. Then, and one more thing, the last factor which we consider is intrinsic wave impedance, eta. The notation is eta. In a medium, it is defined as the ratio of electric field component to magnetic field component. Okay, E by H. For TM wave in our rectangular waveguide, it is eta TM, which is equal to Ex by Hy or minus Ey by Hx. It is the ratio of electric field to magnetic field, either one of these two, depending upon which component is present. So when you take the expression for Ex and Hy, from the field equations and divide them. What is Ex and Hy? We'll go back and see solutions we have obtained. That is that. Here, you have Ex and Hy. So Ex is this. Ex, you divide Ex by Hy, these two. That is the third and second equations. Ex divided by Hy means these cosine, sine, phase factors will get cancelled. A by AO will also be cancelled. Result will be minus gamma by x square divided by minus j omega epsilon by x square. If you take Ey by Hx, then you have to take the fourth and the first equations. That's the only difference. Any one you can take. So when you take Ex by Hy, what do we get? Ex by here Ex by Hy, you get the final when you divide by the amplitudes, you get gamma by j omega epsilon. Eta Tm is equal to gamma by j omega epsilon, and gamma, as you know, it is j beta. So eta Tm is equal to j beta by j omega epsilon. J cancels, it is equal to beta by omega epsilon. Okay, so what is eta Tm or intrinsic impedance? An expression is eta Tm is equal to beta by omega epsilon. See, I have written it there. So we have obtained beta expression before in terms of the cutoff frequency like this, omega into root of mu epsilon into root of 1 minus fc by f whole square. That means beta by omega can be written like this in the next step. So substituting that beta by omega in the eta Tm expression, you substitute it and you get 1 by epsilon into root of mu epsilon into root of 1 minus fc by f whole square. Cancel out this root epsilon and 1 by epsilon. You get root of mu by epsilon into root of 1 minus fc by f whole square. So that eta Tm is equal to eta dash into root of 1 minus fc by f whole square, where eta dash is equal to this quantity root of mu by epsilon. And eta dash is the intrinsic impedance of uniform plane wave in the medium. Now, if the medium is air, if you take it as air, or in general, it is equal to root of mu by epsilon. Mu is mu 0 mu r, epsilon is epsilon 0 epsilon r, for any medium with mu r and epsilon r. Now, if the medium is air or free space, mu r equal to 1, epsilon r equal to 1. So that becomes square root of mu 0 by epsilon 0. You substitute the values for mu 0 and epsilon 0, 4 pi into 10 raised to minus 7, 8.85 into 10 raised to minus 12. So that you will get, when you take the ratio and take the square root, you will get it as 125 ohm or 377 ohm. It is the intrinsic impedance of free space. This is how you calculate the intrinsic impedance of free space. It's a general question also. What is the intrinsic impedance of free space? It is 377 ohm or 125. Okay, you will need this in the calculations. Now, finally, we write Fc once again for TM11 mode, that is dominant mode. The cutoff frequency is Fc TM11 is equal to Vp into a square plus b square raised to 1 by 2 by 2ab. How do we get that? By simply substituting m equal to 1, n equal to 1. Okay, that we have explained earlier. So TM11 is the cutoff dominant mode, and cutoff frequency for the dominant mode Fc TM11 is equal to Vp by 2 into root of a square, root of 1 by a square plus 1 by b square, which we can simplify to Vp into a square plus b square is to 1 by 2 by 2ab. Okay, so we have expression for the cutoff frequency in the dominant mode also. So this is the complete discussion or derivation of factors for TM mode. We will stop here, and in the next class we'll see about TE waves.